Hey everyone, welcome back, and let's write some more neat code today. So it's getting to the end of the month, so you can expect me to be a little bit triggered in this video, but I'm gonna make this problem look so easy you're not gonna believe it. Filling bookcase shelves. So before I even get into kind of, the poorly worded description, I wanted to look at some of these comments down here. I saw a comment that said, I thought this problem could be solved by greedy. Not a hard problem, but very easy to fail in an interview if not careful. And so it makes me realize, oh, this comment is 3 years old. That was before the Leetcode 150 existed, because if you had gone through the Leetcode 150, which is a list of, pretty good problems, I think, that apply to a wide variety of other problems, and if you went down, I think, to a one-dimensional dynamic programming, you'd see a problem, coin change. It's very similar to the problem that we're solving today. It's so similar that it actually fits into a category of problems, which, I've done some course stuff on. It's the knapsack category of problems. And this problem is very similar. And that's the main reason I was able to solve it, pretty easily. So the idea is that we are given a bookshelf. So that shelf has a width, and that is a parameter provided to us. In this case, that width is 4. So in a sense, that's kind of like our knapsack-like container. That's the max that our knapsack could contain, in a way, right? It's not directly comparable, but it's similar. It's analogous. And we also have a bunch of books. That's kind of like coins in the context of coin change. Each book, though, has two things. It has a width and a height. So the idea is that we are filling these books in the order that they appear. So book number 1 is going to go first. And quite frankly, this description, I'm just going to get rid of it to save us space. Okay, that's much better. The idea is we want to fill them in this order: 1, 2, 3, 4, 5, 6, 7. But it didn't have to be like this. Why didn't we just put, by the way, this is the first shelf. So like we have a shelf of width 4 here, and then we decided to have a second shelf here. The width is always going to be the same. It's always going to be 4, but the height of this shelf is variable. This shelf, you can see, is a height of 3. This shelf here is a height of 1. This last one is a height of 2. And so when you add all of those up, you get the total height, and that's what we're trying to minimize. We're trying to minimize this part. And this is the way that we minimize it. This is the correct solution to the problem. But imagine if we didn't do it that way. Imagine if we did this. We have 1, and then we put 2 on the same shelf. Okay, then that has a width of 2, so it'd be something like this. And so now the height of this shelf is 3, and we can't fit this next a book on the same shelf because we have a width of 4 and this one has a width of 2. So the width that we have remaining here is 1. Obviously, this one now has to go on the next shelf. So if we do it this way, you'll end up with something like this, where now we have 3, and then maybe we fit all of these onto the next shelf, or, you could put 2 of them here, I guess, but it wouldn't really save you anything. You could put 4 and 5 here, and then you'd have to put, I think, 6 here, and 7, it has a height of 2. So this way you'll see this is 3, this is 3, and this is 2. So in total, that gave us a height of 8. So literally this first example shows you that you can't be greedy for this problem. When I say greedy, I mean try to fit as many books as you can on the first shelf. When you run out of width, then go to the next shelf. You can't do that in this problem, just like you can't do that in the coin change problem. So once you realize that, and if you have a good understanding of the coin chain problem, it becomes kind of clear that this problem possibly can be solved with backtracking, but most likely we can optimize that backtracking with dynamic programming and then arrive at a very efficient solution. So again, that should be obvious if you have a very deep understanding with the questions in the Leetcode 150 list like I do. So now it becomes a matter of figuring out how to kind of think of that decision tree. What are the choices that we have? Because of course, we're going to have like a pointer I, which tells us what the current book that we're at. And so then one naive approach to take with the decision tree is to track the index I, and also to have a variable which tells us how much space we have remaining in the current shelf that we're at. Obviously, if that space were to reach 0, or if we arrived at a book, the book at index I maybe has a width that is too great to fit on the shelf, then we'd have to then create another shelf, and That's something, again, we'd have to keep track of. And so, of course, the height of a particular shelf is going to be the max of heights of all the books that we placed on that shelf. So that might be something you keep track of here, or, you might do that in the function itself. But automatically, you kind of recognize that this has multiple parameters. If there were a way, like when it comes to memoization with backtracking, if there is a way to reduce the number of parameters, we kind of always want to do that because we can always then optimize the space. And also, sometimes the time complexity as well. But I'm going to show you that we can actually very much do that, and it's very similar to what we did a couple days ago, I think, in one of the dynamic programming problems. We only need a single parameter I. I'll show you why that is. Because we are not, like in terms of the decision tree, we're going to think of it in terms of shelf by shelf, not book by book. Like when we have a decision, we're not thinking, okay, I'm going to put the book here, or maybe I'm going to put the book next. No, we're thinking of it in terms of shelves. So I'm going to say, initially we start at index I equals 0. The choice is this. I mean, we have to put, the one book. Right now we're at an empty shelf. We have to put at least one book there. The decision is if we put book 1 on the first shelf, I'll try to draw it out. It might be kind of hard to do that. Then the choice is, okay, now start the next shelf at index I equals 1. And the shelf, this is what the shelf would look like. The next choice would be, well, okay, now start the next shelf at I equals 2. That would be if we put 1 and this guy on the same shelf. And then the third choice would be, hey, start it at I equals 3. That would be if we put this, and this on the same shelf. But hold on a second, that's invalid. How do we know it's invalid? Well, we're going to be doing something. This, as you can see, we're having a variable number of branches. This kind of indicates that we're going to have some kind of loop within our recursive function, and that's exactly what I'm going to do. And I'm going to keep track of two things. I'm going to keep track of what the current width remaining is in the shelf. So as we loop from 0 to whatever index that we stop at, we're going to keep track of the current width. The width starts at the parameter, whatever shelf width is. It started at 4 in this case. Every time we added a book, we decremented from it. So -1, okay, here, -2. We have a space of 1 left in this width. So we're going to keep track of that. That will tell us that, okay, we don't actually have enough space for this to be on the same shelf. So that will tell us when we can stop. So we'll have these recursive cases. Another thing we have to keep track of is among the books that we did place on the shelf, among all of those, what was the max height of them? Because that's going to determine the height of the shelf. In this case, we only had 1, so the max height was 1. In this case, we had this and this on the same shelf, so the max height, of course, was 3. So we have to keep track of that. And then with this max height, the sub-problem becomes obviously the recursive case. So we already recognized that this one was invalid. So I'll kind of continue the decision tree from here. So here, I equals 1, the choice would be, okay, now start the next shelf at I equals 2, or I equals 3 in the context of this problem. I equals 2 would basically say that this is by itself, and then this guy is going to go on the next shelf. I equals 3 would say that these two are together, and then this one is going to be on the next shelf. And we can't really do I equals 4 because we wouldn't be able to fit this on the same shelf. So these are the only two choices in this branch. And so I'm just going to continue with this side because I know that's the correct answer, but I want to show you how the recursive call, like the return value of the recursive call, is going to play into calculating the result, because that's kind of what dynamic programming or memoization is all about. It's called the recurrence relation. So I want to kind of make that clear to you. So here, I equals 3. So for the record, I equals 3 is the index. So this was at index 0, this was index 1, this was index 2. So 3, this is the book on this shelf. This is the first book on this shelf. So here, obviously we could say I equals 4, I equals 5, I equals 6, and we could even say I equals 7. But 7 is an index that's out of bounds, actually. So this is the base case. This is where we don't have any books, and this is the case where we put all 4 of these books on the same shelf, so that the next shelf would be at this index, but that's out of bounds. So this is the base case where we would return 0 up to here. And then from I equals 3, if we put all of these on the same shelf, the max height of them was 2. So 2 is what would be returned up to this guy. This guy put these 2 on the same shelf. The height of that was 3. So we would take the 2 that was returned here and the 3 from here, add those together, and then return up to the parent 5. And then from here, we only had a single book. The height of that was 1, so add 1 to this 5, and that's how we got 6. So conceptually, this might have seemed complicated, but I bet when I show you the code, it's going to be not too difficult, and I'll analyze the time complexity there. But I will tell you that this is actually the most optimal solution. You don't need bottom-up dynamic programming to arrive at the optimal solution for this problem. Okay, so I'm going to create a recursive function called helper. We're going to keep track of the current index that we're at. The main base case, remember, was I equals length of books, where we don't have any books remaining. So the height of all of the shelves in that case is going to be 0. And then we're going to start looping. We're going to go for j in range starting at I up until the end of the books array. But remember, we might terminate out of this loop early, and I'll show you how we do that. Remember the 2 things we're keeping track of: the current width, which initially is always going to be the shelf width, because every time we start a recursive call, we're going to assume that we're on a brand new shelf and it's going to be empty. So this is the current width. We're also going to keep track of what the max height happens to be among all of the books that we put on this shelf. Initially, we'll say that that's 0. We're also trying to minimize the total height. The result, I'm going to initialize to be very big, infinity in this case. So now I'm going to get the current book, and just for readability, I'm going to do this. So books, I'm going to unpack it. I'm going to get the width of the current book and the height of the current book. And before we even try to place this book, let's just make sure we have enough space for it. Let's check, is the current width less than the width of the book? Like, this is the space that we have left. This is the width of the current book. So sorry if this is confusing with the variable names, but if this is the case, we don't have enough space. So at that point, we have no choice but to break out of the loop. Otherwise, we do have enough space. So let's just try it out. Let's first update the current width by doing this, subtracting the width of the book. And let's update the max height potentially by setting it to the max of what it currently is and the height of the current book. Now is for the recursive call. And I guess I didn't explicitly talk about this in the drawing explanation, but given that we're trying to minimize the height of the shelves, it's in the context of the problem. I'm sure you can guess that we're going to need a minimum somewhere in here. And so we're going to try to minimize the result. So take the minimum of itself. And this is where we put the recursive call. We're going to do helper. So if we included the book J, we're going to say this is the last book that we put on the current shelf. So let's try starting the next shelf at J plus 1. Let's just try it. But with this, we have to add to it the height of the current shelf, which is going to be the max height that we've seen so far. So with this, I'm going to add the max height. And that's pretty much it. So I'm going to zoom out a tiny bit. We're going to need a bit more space. Here, we're going to return the result. That's pretty much it for the recursion. Down here, we're going to call our helper function, as you can imagine, starting at index 0, and that's what we're going to return. The only thing is, though, we haven't really added caching to this yet, but given that we only have a single parameter, it's going to be pretty easy to do so. I'm going to have a cache here, which in my case is just going to be a hash map. Here, I'm going to say if I is in the cache, we've already solved this subproblem before, just return it. And what exactly is the subproblem? Well, it's telling us if we start a shelf from index I, what's the minimum height it would take to fill the remaining books from the array? And that's what's being cached here. So down here, I guess we can replace the result with the cache value. So cache of I will initially be this, and then down here, we can return cache of I. So that's pretty much the whole code. It's about 24 lines. And actually, I think we forgot to update result here and here. So let's just make sure that we do that. So I'm going to copy that here. And I'm going to copy that here. Hopefully we didn't miss anything. Let me just confirm that this works. And as you can see, it does, and it's pretty efficient. This actually is the optimal time and space solution. So let's quickly analyze that. Firstly, it's clear that this recursive function is going to be called n different times, for like once for every book. And once it's cached, it won't be like repeated work or anything like that. So what exactly is the time complexity of this loop? Naively, you might think it's also the length of the book. So if that were to be n, you might think that this is an n squared solution. But let me tell you why we can get a more precise time complexity. We can actually say that this is big O of n times whatever the shelf width is. Let's call it W. And the reason for that is we assume, first of all, every book is going to fit within the shelf. Like any book is never going to be wider than a shelf width. But at the same time, every book is going to have a width of at least 1. So this loop can't possibly run more than this many times, because if every book has a width of 1, we will break out of the loop before we go through all the books, right? I think that makes intuitive sense, and in most cases, the books are going to have a width larger than just 1, so this loop won't run n times, it'll run this many times in the worst case. So that's the time complexity. Space complexity, you can probably tell, is going to be O of n from the recursive call stack and also from the space that the cache is going to occupy. I was mentioning that this solution might look complicated to you. I'm not saying it's easy for sure, especially if you're not familiar with coin change and some of the other dynamic programming problems I've talked about, but let me just show you. I mean, first of all, this is Leetcode's recursive solution. I mean, a long explanation, but maybe some people prefer that. I don't know. First of all, their space complexity is not as good as mine, and my God. So it's about twice the length, and it's about twice the complexity as well. I mean, look at all these variables that they're passing in. I mean, they didn't make it a nested function, sure, but the reason their space complexity is less efficient than mine is because you can see that their cache is actually 2-dimensional. Mine is 1-dimensional because, sometimes the people writing these Leetcode editorials are just not as good as, some of us. I'm sure many of you guys watching could probably write a better one than this. And so then it comes down to the bottom-up solution. And thankfully, the bottom up is actually very, very trivial to come up with once you have the recursive solution. Let me show that to you right now. We actually can, at this point, pretty much turn off our brains because now we've realized that the solution space is going to be of size like proportional to the length of books. So I'm going to say DP is going to be an array initially filled with all zeros of length books, but I'm going to add a +1 just for the out of bounds case where I is equal to like the out of bounds index. In that case, we want to return 0. So that's why I'm doing the +1 here. So now I'm just going to compute the result of the subproblems in reverse order. I'm going to say for I in range starting at length of books -1 going in reverse order. And then I'm pretty much going to turn off my brain at this point. I'm sorry if you expected an explanation, but I'm not going to do it. I'm just going to copy and paste this because it's literally the exact same. Because now we're asking, like we're trying to compute dp of I. So instead of calling this cache of I, I'm going to call it dp of I. And dp of I is going to represent the same thing that it did in the recursive solution. Like starting at I, if we had an empty shelf, what is the minimum height it would take to fill the remaining books starting from index I? So again, we're going to have to keep track of the max height of that as well. J is going to do the exact same thing. We're going to get the width and height of that book. We're going to check that we have enough space for it in the current shelf. We're going to update the current width by subtracting the width of the book. We're going to update the max height the exact same way. This time, we're just going to replace DP or cache with DP. Same thing over here. And helper, of course, we're not doing this recursively, so what should helper be in this case? Yep, you guessed it, dp of j plus 1, because that is the subproblem. And I might be forgetting to do one or two things, but remember that with our recursive function, we were returning helper from 0, and we're going to do the exact same thing here. We're going to return dp from 0. Now, there's no way to optimize the space to get it down to constant space because as you can see, to compute dp of I, we're going to need potentially every single value that came after dp of I. So there's, at least as far as I know, no way to optimize the space. But I think this is correct. Let's run it. Yep, as you can see, it works as you'd expect. It's just as efficient in terms of time and space. But, some people prefer the bottom-up approach. It looks like it took us about less than 20 lines to do it. If you found this helpful, check out Leetcode.io. I'm not joking when I tell you that 150 problem list will absolutely make you better, especially if you can actually understand each solution. And of course, I have a bunch of courses that can teach you all this Python stuff and also like the fundamentals of data structures and algorithms.